Um, Welcome to the third MSSE Industrial Seminar Series this fall. I am Sanjay Rajithan, Director of Software Engineering Center. I'm standing in for Kevin Ment, who normally runs this. Today it's my pleasure to welcome Stachour, who has been in this field for
over
50 years. And he has a long history of working in critical systems, developing systems with high assurance, and much more. He's going to walk us through the concept of compartmentalization and how it's been evolving over the years, what's worked in the past, what's not working, and some ideas for future. I will let Paul introduce himself to give us brief history, his work, and then take the discussion. So take it away, Paul. Thank you.
Thank you, Sanjay. So let me begin by saying that I went to college to become a high school math teacher. I got put into an experimental first class in assembly programming ever taught at the school where I was studying. And I effectively got waylaid into computers and worked there for my entire career, spending a lot of it in life-critical systems. I worked for the computer manufacturers, IBM, Honeywell, and Secure Computing. I worked for Delphax Printers, Boston Scientific, Honeywell Aerospace, Net Perceptions, and Detector Electronics, to say a few. I'm mostly retired now. Still do some software quality assurance work. I did 150 tax returns last year. That's one of my part-time gigs. I work with the Toastmasters, helping people learn to speak, teach a little bit of partner dancing, and from a personal point of view, I'm studying Japanese, and I'm also working on learning the state-of-the-art of proving programs correct with Ada Core and Ada. So let's move on. I'll move to the first slide. We're having a technical difficulty moving to it. So while he's working, let me just say that many systems are not designed and built with compartments correctly. And to allow me to begin with a somewhat radical statement, as Sanjay's bringing the slide up, malware exists today and accomplishes its objectives only because we don't use proper compartmentalization techniques. And I will show two systems that I worked on and with, which were properly compartmentalized and have been in existence for over 20 years without any break-ins, and why those weren't there. So there's our ransomware as a problem slide. Very good. Now let's move on to the next one. So let's take an example of compartmentalization, trenches, as they're used in warfare. To assist in the prevention of attacks, they built trenches against the tanks. However, when they started to do it, they discovered that if the trench was straight on and the enemy came in, they could fire right down the trench and take everything out. And so they learned to build the trenches with corners in them that effectively were the compartment. This ensured that when an enemy took over one section of the trench, it did not have automatic access. Okay. Sanjay has a moment. Trying to get me in focus on it. By the way, if you're here in the classroom and you want to ask a question, just sort of raise your hand and signal so I know to stop at the end of the paragraph. If you're online with Zoom, raise your Zoom hand so Sanju can, we can call on you at an appropriate time. Okay, I see we've gone to the next slide. Here's my example number 2 of compartmentalization. Here's one that was built with a significant number of compartments. The Titanic was said to be unsinkable because of the structure of its watertight compartments. Even if water tubes were breached, the rest would hold, and there would be enough air to create the buoyancy needed to keep the ship afloat. Now, in this case, the ship went down. 6 compartments were flooded, and water went over the top of the compartments. It was presumed that the ship would remain level. And when it wasn't quite level, eventually the compartment barrier was breached. And that's one of the things we have to think about the compartments is how do we keep the barriers as well. Next slide. Here's a picture of Multics from a marketer's point of view. The GE, MIT, AT&T, Honeywell Multics operating system was properly compartmentalized. In about 20 years of operation in the public community, security was never broken. We'll discuss Multics and its compartmentalization in detail later. So let me back up a moment and give you a definition. Next slide. As I do it, what is a compartment? And I see we could have had a little bit better text in here to read, but a compartment is an entity that contains data that is made accessible to other entities under some conditions. That is, it's not automatic. Why do we need compartmentalization? Well, I was hoping for a group here where we could break into small groups to discuss the questions on the next slide, which are, what compartments are you familiar with in today's operating systems? How successful are these compartments? And why do we need compartmentalization? Okay, so for those of you in the classroom, how about some thoughts? Or for those of you on Zoom, drop me something in chat.
Well, one compartmentalization I work with all the time on my job is the sandboxing that Apple applies to apps on your phone. There are certain ways an app can interact with the system and certain ways it just can't.
Okay, so for those of you who are out there, someone in the classroom talked about the sandbox in the Apple operating system. And certainly, there are browsers that have sandboxes too.
Not exactly operating system, but the concept of containers running, like Docker containers, are kind of sandboxing of, whatever you put in it to run in its own kind of sandbox-like operating system environment.
Okay.
Alongside other ones.
So here in the classroom, someone talked about Docker containers, which effectively can be separated from each other and from the rest of the system.
I have one in the chat. Java applets are designed to be run in a browser compartmentalized.
Java applets are designed to be run in a sandbox. Those are good examples. Okay. So let's move on to the next slide. And we'll talk about some examples of compartments. And this is one where it shows the piece to make you different. So we'll take the first one. So things like magnetic tapes, disks, USB sticks, compact discs, those are compartments. Right? A paper file folder or a computer system file folder. A tape drive, a disk drive, communications control. A computer memory, if being able to restrict access to words, pages, or segments. A file, a spreadsheet, a database. A single isolated computer and all of its devices. Or a group of computers on a network where the network is isolated from the other networks.
There is one more on the chat about security chips separated from primary processor. Do you think of that as a component? The security
The security processor chip
separate from.
that's monitoring the other process. Yeah, so that's, shall we say, an extension of virtual memory thoughts in the idea. Okay. Okay. So how successful are these? Sometimes they're really successful and sometimes they're not. The question is, can you break through the boundaries on compartments? How well are they? We need them to protect users against other users, to protect the operating system from users, and also importantly, to protect users from the operating system functionality, something in the other direction that's not often thought about. And of course, protect against rogue people and their rogue programs. And to minimize the damage that can or does happen when there's an error or break-in. If we understand that compartmentalization is important and that we work things between and across compartments, what would be the characteristics of good compartmentalization? First of all, that we can name the compartment so that we can therefore identify it. That we can place permissions or conditions on the compartment as to how it can be accessed. That we're not limited to a single permission factor, but that we can actually have multiple permission factors or multiple ways of enforcing the compartment. But we have to look at the opposite side too, is that we have to have those compartments that are shared. That is, an open compartment can be shared by other processes. So we can't make our compartments too tight, because as we'll see in a little while, if we do, then we have some issues associated with it. We like to have the ability, under the right conditions, for processes to transition between the compartments. And last of all, the list of the cost of moving data and content between compartments when we need to do so should be low. In other words, our isolation shouldn't be too strong. Next slide. So now I'm going to talk about compartmentalization as I see it and some early compartmentalization. And I'll do so by walking through the systems that I used as I learned computing. And that's how we'll see what some of the compartmentalization. Let me tell you about the first system that I ever used. It was in 1963, and it was a tape-oriented IBM 7074. One prepared their program on punch cards, as along with a small set of data on punch cards. An IBM 1401 was used to copy the cards to the tape in batches. A switch was thrown to make the tape accessible to the 7074. The 7074 OS was booted from a separate tape. The OS read the jobs from the tape one by one, compiled and ran the programs, writing the outputs to other tapes. The 1401 was then used to copy the output tapes to cards or to print as appropriate. Note that no program had any opportunity to affect any others, as only one program was in the machine at any one time. In terms of compartments, the tapes acted as a file barrier between the various parts of the system. Bad effects were 100% prevented. Data moved across the barriers effectively and efficiently with the needed speed at that time. Okay, so how does it work with regard to compartmentalization? Well, if we look at our factor scorecard, we see it scores pretty low on everything, and the transition time takes minutes. So here's a pretty good compartmentalization. Why don't we use this method today? In the classroom or on Zoom?
Slow.
Well, not here anyhow, Frank.
It's slow.
It's
takes too
slow. Yeah, by today's standards, it's really, really, really slow. And it was also quite expensive by today's standards. Yep. Let's move on to the next slide. So you're right, dedicating the whole very expensive computer to just one task didn't do it, and it was very slow. One could get more bang for the buck by running multiple jobs in a single computer at once. But how do you keep them from interfering with each other? One method used was having a key, which you'll see on the screen, for each block of memory. This leads us to the architecture of the IBM 360. Next slide. So here's a summary of some kinds of memory separation. And that was what was recognized of what was needed. The only one we're going to talk about is the key. They built the 360 in multiple sizes and multiple speeds to get around the expense problem. In the smallest version of it, you ran one program. PCP, they called the variant of the OS. In the slightly bigger one, they called MFT, and you had to partition the memory and you could run a task in each memory. And MVT actually allowed you to change the sizes of what went in the various pieces of memory. Now, this was all physical memory, and the keys allowed the programs to exist and not be able to move. But the sum total of the number of keys was 15. So that was the maximum number of programs that you could run. And when you did that effectively, you couldn't use all the computer memory for a single program. The OS ran in key 0, which enabled it to read and write user program memory. while preventing the user program memory from writing into the OS. How does this system perform when looking into the compartmentalization? Next slide. You didn't really name the compartments too well. The permissions were by single keyed memories. It was user to OS only. Process switching was the way we took care of it. And we had some medium level of performance. Any thoughts or comments before?
I have a question. So when you say performance low, medium, like what's the basis or reference point? Say what is low and what's medium?
Well, so that basically, as we go from low to high, the amount of time necessary to move between compartments gets less and less. I don't have any quantization levels.
Just orders of magnitude, like are we talking milliseconds, seconds?
We're talking sort of orders of magnitude, but not anything specific. I don't have any specific measures, either in this system or based on my experience. Okay. So we did have a little bit of discussion. Let's move on to the next slide. And I wanted to get a really good quote from Weinberg, and I hunted for it, and I couldn't find it. Eventually put this one in, but let me take the similar one, which is Gerald Weinberg, by the way, was one of the first people in computing to get a PhD. He's got a double PhD in psychology and in computer science. And he wrote The Psychology of Computer Programming. We have to think about correctness. And one of the first jobs he did, he was yelled at for making it too slow. And he said, yes, but my program gets the right answer. If it doesn't have to get the right answer, I can make it go as fast as you like. And the same thing is true for compartments. I'm going to move on. The IBM 360 was replaced by the IBM 370. Same instruction set, only it had virtual memory and replaced swapping with paging. This solved many of the memory sizing needs at the cost of increasing the total elapsed time to run programs. When we were doing swapping, one of the things that the programmers did is they organized their programs based on the things that ran together in time were packaged together physically in space. And so therefore, when something was swapped in big chunks, but never had to wait for memory while the individual piece was running. In the 370, we had virtual memory and solved the memory sizing need. However, there is some compartmentalization programming in main memory. There was no thought to compartmentalizing other resources such as disk files or removable memory such as magnetic tape. Nor on that operating system was there any definition of an entity such as a user to separate the activities of one person or group from that of another person. So in that same time frame, I had the opportunity to use still another operating system. I used CP67 and VM370. These were individual virtual machines running on one physical machine. One had a user or a user ID associated with each virtual machine. And there were virtual shareable disks, but no mechanism to control the sharing of smaller items, such as files. Other than read-only sharing by the VM monitor of VM disk, there was no sharing between the users. So if we look at the compartmentalization available in VM370, it was easy to name the compartments. There were named disks, permissions by the users, but still only a single permission factor. Sharing was by the virtual disk. And again, we did a process switch, which gave us some medium level of compartments.
It's a single permission factor. Does that mean get it or don't get it? Not what do you mean by single factor? No read, write differently.
That's right. There was only one thing that you could do. That's a user. So I could share a disk with you, read it. I could share a disk with you, but I couldn't create a group. I couldn't put any other characteristic on the sharing. And also, the only kind of sharing there was read sharing of the disks. I couldn't do any write sharing of the disks. They didn't have the ability to effectively lock the disks for one virtual machine or another virtual machine to prevent two of them trying to write the same lock or same parts or different parts of the system. Okay, good. Any questions, other questions in the classroom or on Zoom at this point? Are we ready to move on? Let's go to the next slide. By the mid-1970s, the idea of many people sharing one computer simultaneously as a computer utility had come to the forefront as an idea. It was understood that all of the people working on a given computer system would not necessarily be cooperating. Indeed, some very well might be at odds with the other people on the computer. The U.S. Department of Defense was concerned enough about computer security that they created a series of books. In other words, requirements. It was called the Rainbow Series because each book had a different color on the cover. This describes some of the features and functions that should be present or that should not be present in order to make a computer system secure. If you've never read the Orange Book for single systems or the Red Book for networks, I encourage you to do so. I have a picture of the Red Book. Let me go back one. I have a picture of the Orange Book on this slide. I went to my garage and tried to find my personal copy of the Orange Book because I wanted to bring it in and wave it. Unfortunately, my filing system of old materials is not as good as it should be. I encourage you to do so. The books indicate the kind of things that are needed. And there are copies of them available online. Ready to move on. So I studied at the University of Waterloo in Ontario in the mid-1970s. I was fortunate in they had generally available to all of the computing systems, not only the Lot 4 series of Fortran compilers that ran in a specialized partition in OS 360, they also had an IBM VM370. They also had a PDP-11 running Unix and a GE Honeywell 6000 running GCOS 3 and later GCOS 8. It was on GCOS that I was introduced to what reasonable separation, sharing, and compartmentalization should be, and what general and specific permission should look like. So this slide here shows multiple people. They're using a laptop in the screen in this slide. But of course, in those days, what we had was 24 line by 80 characters CRTs. And the other side of the slide shows files to indicate that we could share at the named file level. And as an example of the kind of permissions that are really good and that we had then, I could on GCOS give someone recovery permission on one of my files. So that meant that if the file got damaged some way, that person then had permission to run a command which would reference the archive of saved files on tape and bring that tape back to disk, while giving them no ability to make any other changes to that file in any other way. A second example of permissions that existed on that system was append permission. I could give a number of people append permission to a file, which allowed them to write at the end of the file, but not to write anyplace else. A great place for keeping logs, complaints, anything like that. This allowed me to write a general purpose program runnable by many users under their own names and permissions that logged its actions whenever it was run, with no way for anyone else to corrupt or modify. Let's take a look at the scorecard for GCOS. It was easy to name compartments that we worked with, which were files, and for users to provide permissions on the system. There were no way to do multiple permissions, well, multiple users, but there was no such thing as a group concept or any other concepts. The sharing could be done with regard to the modes and permissions placed on the file, of which there were, my memory, about 8 of them, and transition by the CPU being dispatched, and the fact that you actually could have, and this was my first experience with multiple CPUs running in a single memory, 2 memories or more, but the performance, again, because of that, was sort of. Questions, comments? Hearing none, let me move on to the next item. I worked I then worked at a company called Secure Computing. The Orange Book gives levels of security, A, best, B, C, etc. And numbers them 1, 2, 3, 4, with a higher number being better than a lower number. Multics, which we'll talk about in detail, was B2. Secure Computing built a system that was intended to be used in a place where the federal government had to provide secure data in a place which might be unsecure. In other words, we weren't going to provide the computer in a locked room. We were going to provide it in a place that might be a problem. Specifically, the target for this computer system was consulates of the US federal government all over the world, whereby someone might break into the room and steal the computer out of the room. And yet there was a need to place highly classified data onto those systems. So what we did is we designed and built a specialized system intended to be certifiable at the A1 level of computer security. It was a Unix-style OS with some capability architecture features for compartmentalization. The CPU on this was a Motorola MC68020 with a specialized MMU chip. Our chief security person, Earl Bogert, has had a very good series of documents which we have written, most of which were classified at the time. I understand they're unclassified now. I was not, however, able to find them in my search. Where we had created a specialized MMU chip with an execute-only function. This meant that there was no way for users to examine the program with a disassembler or any other tool to see what it was the program did. We built and sold about 100 of them to US consulates around the world. And a second compartmentalization mechanism in that system was that our disk was encrypted. That was something new for that day. So the encryption key on the machine was in a very, very small read-write chip inside of the machine. And the key for there was the encryption key was loaded from an external key that was brought and placed on the machine and then taken away. So that the only place the encryption decryption key was on that chip. Along with that, there was a red button under glass, broken, so that if somebody broke into your building, you would simply hit that red button. It would destroy the encryption key on the chip, and then everything on the disk would be useless. Well, not completely, because if they didn't carry the computer away, you could later bring the key back from where it kept and do it. We built about 100 of these, and I would say it was a very successful compartmentalization. However, we did have a problem. The problem was that chips got smaller and smaller and more highly integrated. And Motorola, which at the 68020 had their memory management unit on a separate chip, which we were able to replace, now brought it inside the CPU chip. We couldn't replace it. We couldn't create an appropriate memory management unit. And so therefore, we were out of luck from building or doing it. Let's move to the compartmentalization factor scorecard. For this, we compartmentalized things at the file level. We had multiple permissions on users or groups, which gave us multiple permissions. We had sharing on the file nodes, especially read, write, and execute, enforced by the memory management unit. We could transition things by dispatching the new processors. And again, we have a reasonable amount. All right. Questions here before I move on? Let's go to the next slide. By the way, I'm sure Locke is aged out by now, and there are none of them left in the world. So we moved on. I worked at Net Perceptions, which had a recommendation engine. And this picture is intended to show that there were users out on a network who used it, and that the system itself was built around the network. The recommendation engine got called from a sales application as or after a user had indicated a product to buy or potentially buy, and it then provided a recommendation as to some other product that the user bought. We couldn't run it when we started by running the recommendation engine on the same computing system that the front end to talk to users was, nor could we run it on the machine where the database was, because the database was owned by our customer. So for example, JCPenney or Sears. And the recommendation engine had to get access to their products sold and whether there were any available for sale at that point. So this was the compartment separation we have on this system. The user at the other end, looking at it, typically would not wait more than, say, 3 seconds to see a recommendation, or they'd move on and nothing would happen. And so our problem was that we had good compartmentalization to get some performance from the various pieces, but our transition time to send the messages back and forth that were necessary between the computer systems was long enough that we couldn't get enough performance out of it to make it a good product until the technology was such that the systems were faster. We were then able to move things to a single system meeting our performance objectives, but losing our compartmentalization. And we wanted to keep the compartmentalization. Eventually, everything was brought onto, except for the end user interface, was brought onto one computer. Let's look at the compartmentalization factor scorecard for that system. Could we easily name and share our things? No, we didn't. And we didn't think it was necessary. We didn't have any internal permissions. We simply had separated the pieces. We didn't have multiple permission factors. Sharing was via messages, as were our transition between compartments. And as a result, our performance was low, and we really didn't do what it was that we had set out. Questions or comments on this? I'd like to move on to the next one. Oh, let me finish something before I do it. Today, if you take a look out on many systems, they use many virtual machines to give them their compartmentalization on a single physical machine. However, the sharing model of the virtual machines is not controllable at a measurable size of item. So it often too can fail the performance test to do the compartmentalization. I'll talk about how Multics manage both a little bit later on. Ready to move on to the next slide. So here's an example that I think was a success. I worked at Detector Electronics, which was a fire and mitigation company. We see on this slide 4 items. One is a fire detector in the upper left. One is a sprinkler system, a mitigation in the lower right. We see a controller on the lower left. The control set works with the detectors and effectors. And on the right side, we see the upper right, we see the preparation system, which is also used for launch. So let me talk a little bit about the 2 devices, that is the fire detector and the mitigator. Well, how did we build those? So our first compartmentalization, as I said, was those 3 physical components. And each physical component had 2 processors inside of it. One was the processor that basically did the work. It detected the fire. It sprinkled the water. The other was the communications controller that talked to the rest of the system. And there was a small communication inside the device that did it. Let's move to the next slide. All of the detectors, effectors, and notice the 2 controllers were connected on a network. This was a very specialized network. Notice that it is a ring. It is not a star. Okay? And the ring contains at a minimum 2 wires. And so the messages can go either direction on the network. And that if the wire is cut at any one point, it does not result in loss of communication. In addition, the communication through each device was designed and built in such a way that if there is no power on the device, the message effectively just goes through. If there's power on the device can read the messages and also can break the communication to add its messages. In addition, each item had power from 2 sources for reliability. And that gives us our second compartmentalization. But one of the key factors was the connection between the preparation and monitoring system and this long range, which went only to the controller item and not to any others. Okay? So if we look at it from a read-write point of view, in normal operation, data could only pass one way, that is from the controller to the monitor. The monitor could ask for certain kinds of data. However, it could not make any changes whatsoever to what was being looked for or how often things were checked or to turn on or turn off any mitigation device. So while we had physical two-way communication, it was compartmentalized such that logically the communication was only one way. So let's suppose that this detection and mitigation ring is at the Northern Natural Gas Distribution Facility in Grimes, Iowa. But that our preparation and monitoring system actually runs over the internet to the Northern Natural Gas Facility monitoring systems here in the Twin Cities. Sometimes you do need to make a change. And so the way we handled this and compartmentalized it is we recognized that when you make this kind of a change, there should be somebody present to make sure that it's done properly. So that one has to push a button on the physical controller to momentarily, well, for 3 or 4 minutes, open up the ability to write new controls, and it automatically turns off as soon as the control. So I would consider this an example of successful compartmentalization that we did. Let's look at the compartmentalization factor scorecard on the next slide. It was easy to name the individual compartments on our log. They're the device IDs. The permissions that can or can be done was done by a graph that was built on the preparation machine. We only had one way of handling that permissions, and that was the activation of the download by sending things on messages. And again, our performance in doing that and making the changes. Okay. So at this point, that sort of says, hey, here's mostly what I have. And before we move into talking about the other very successful systems that I worked on, I'd like to do a little bit of discussion. Okay, next slide. And you should ask yourself, what's the security policy of today's client server or cloud computing applications you work on? How can you find out what it is? How is the data protected? Who can see your data in normal circumstances? And who can see your data in case of error? Can I grab the chair? All right, Sanjay says I should put this on. Comments, thoughts from anyone? Can they still hear me out on the net, okay?
We'll try.
Okay.
I don't know how is the audio coming because there's a lot of background noise with the fan.
All right. So I want you to think about those discussion points. Any thoughts or comments from people in the classroom or out on the net at this point?
Well, from the client point of view, from the user's point of view, a lot of these are not really knowable because the host, whether that's Google or Facebook or whatever, just gives me what they want me to see. So how are my Twitter posts protected? I can't find out.
A very important item shared here in the classroom. On most of today's client server systems, whether we're talking about Google or LinkedIn or Facebook, they don't publish a security policy. They don't say what it is. Whatever it is, how they share or what they share is not that easy or maybe even possible for you to find out. So that they say we share things with friends or whatever, but what does that mean? We really don't know. One of the things that I liked about the areas where I worked, for the most part, although there were places where, is that there was a published security policy that said, this is how our system works, this is how we share, and here's how you can find out what the sharing policy is with regard to any particular kind of item, be it a file, a disk, whatever it is that we allow sharing on. So we were able to see what the compartmentalization was. Maybe we couldn't control it as much as we would like, but it was there. Am I too low or can we're okay? Okay.
I was going to ask, like, I mean, whenever you sign up for a service, you look up, pick on all the terms and conditions and the privacy policy. So there is something that's put out which says this is our data sharing. You consider that as not sufficient or not actionable? Or?
Well, I consider it not sufficient, and because all it really says when you read it is, for the most part, any data you give us can be shared. It says that you you have no way of indicating certain things that are shareable and other things that are not shareable. It also basically says that everything you put in or that they can discover about you, they can share with anybody they want. And it says nothing about how things are managed within their system to ensure that if somebody breaks in, that they can only get pieces. Now, if I look at one system thing that I use while I was at Detector Electronics, it was our change management system with regard to errors and defects and items you want. But every individual change notice could be individually controlled. Okay. So today, if I go to, let's just say, Facebook or LinkedIn and put in 3 opinions, I can't say, Steve can see this one, but you can't. Or you can see this one, but Steve can't. Okay. So the level, the breakdown, the size of the things that can be shared is such that it effectively, I'm going to say, is close to useless in that manner. I'll come back a moment to what I was starting to say about the defect management system. So if I found a defect and I put it into the defect management system where there were all sorts of records about things, I could see it, and automatically whose ever component was associated with could see it. So with regard to the fire detectors, the fire detector people could see it, but the mitigation people could see it, and the people who did the controllers couldn't see it, unless I effectively said, yes, you can see that. In addition, and this was a feature of the system that I liked, if someone needed to work on an item, okay, maybe there was somebody in the mitigation group that needed to see something about this item that was against the fire detector group. As soon as it got assigned to that person to work on it, they automatically had permission to look at it, but nobody else in the group did. So the controls were very flexible, yet fairly solid as well. Okay, any other questions or comments at this point? Okay, let's go to the next slide. I am going to declare a 5-minute break roughly. It's now, by the clock here, 28 minutes after the hour. Let's make it 35 minutes after the hour. We'll come back, and in the meantime, grab yourself a coffee or a Coke, or I see there's some fruit bars in the back, or take your restroom break or whatever. Thank you for that. And Sanjeev, were you wanting to get a list of people in the room? discovery of natural gas here. Cough drops. We're now on. Okay. The second part, I'll be talking about Multics. Multics is a successful compartmentalization. And let's have our first slide, please. So I had the good fortune to use Multics for more than 10 years while an employee of Honeywell here in the Twin Cities. Multics was designed to be the operating system on which you could run a computer utility. That would mean that there would be multiple users on the same system who would have competing objectives. These users had to be protected from each other, as well as the operating system had to be protected from the users, and the users be protected from the operating system. Security was a fundamental design requirement in order to meet the utility goals. In my opinion, Multics, which stands for Multiplexed Information and Computing System, was the best operating system ever designed. Its detractors chuckled when they called it many unnecessary launch tables in core simultaneously.
Sorry, folks. I have to restart the meeting session here.
Okay. We're having technical difficulty again.
I cannot see anything on Zoom. People are saying things that
So welcome back. We've had some technical issues which looks like we've solved. So this second portion talks about a successful compartmentalization, namely Multics. I had the good fortune to use Multics for more than 10 years while an employee of Honeywell here in the Twin Cities. Multics was designed to be the operating system on which a computer utility would be run. That means there'd be multiple users in the system who would have competing objectives. The users had to be protected from each other, as well as the operating system had to be protected from the users, and the users protected from malfunctions of the operating system. Security was a fundamental design requirement in order to meet the utility goals. In my opinion, Multics was the best operating system ever designed. Multics stands for Multiplexed Information and Computing Service, and the chuckle is that its detractors called it many unnecessarily large tables in core simultaneously, because a lot of what it did was actually table driven. It took advantage of specialized virtual memory hardware. This virtual memory segmentation is the key to everything that Multics is able to do. The hardware also had integrity instructions that enabled the loading of a particular element of an array with an automatic hardware fault if the index was out of bounds. It also had the ability that if you tried to access a segment that currently was not mapped, it took a hardware fault. And if conditions changed with respect to that segment, one could set a bit in the segment register, which told the system to go out and recalculate it. Multics was written almost entirely in a fully defined high-level language, namely PL1, that totally prevented almost all of the out-of-bounds errors so common in software today. It enabled switching between compartments in one instruction. It allowed programming one compartment to execute an instruction in another compartment with the security controls of the other compartment. Administrators and system-level programs had zero access to any user data unless the users added permissions to allow that visibility. There are hundreds of documents comprising almost all of the documents written during Multics on the network site multicians.org. They define the objectives of the system, design, implementation, verification, the problems the developers faced, how they solved them. They describe the issues and problems discovered while they were building it. They describe the wrong starts, the bad solutions, the mistakes they made and how they were overcome. They describe the security flaws they found during development and how they fixed them. I note that no exploitable security flaws were ever discovered during the 20 years or so that Multics was available. Unfortunately for us, Multics has aged out. It's no longer available, except there is a hardware simulator and a full virtual boot tape that you can put on an appropriate system where you can learn and experiment to your heart's content. Yes, I have my personal copy of many of the manuals written about Multics, as well as a copy of the simulator. let's look at some of the elements provided. The first one is the virtual memory, which we've shown here on the screen. Everything on the system was a virtual memory segment addressed through a segment and page table. Everything, including the I/O and communications processes, ran in and was constrained by the virtual memory. Everything had to be mapped into a virtual memory segment, which was the unit of access control before it could be referenced. The second aspect of Multics was the rings. The picture here shows us with 4 rings. Multics actually had 8 rings. Okay, numbered 0 through 7. A program running in the memory of a lower ring had access to objects in a higher number ring. There was no access, except in extreme sufficient conditions, which I'll talk about, in the opposite direction. And the access control lists were ring specific. That means that one could give the world access to a database in ring 4, but the user program was running in ring 5, where it had no access to the database, except through a gate segment. That's the only way it could get there. Let's look at a gate segment on the next slide. A gate segment was merely a piece of ordinary executable code with something at the very base of the segment having a number. The number was the number of gates in that ring, in that segment. And the only way you could cross into a lower numbered ring was to call a program where that number was non-zero. It then had the gate addresses and the executable subroutines. So that meant that if I called one of these gate segments, I could only start it at a subroutine which was defined to be accessible from an outer ring. And all other subroutines were only accessible after one is executing in that gate segment. So the effect was that the data residing in that inner ring was completely protected from all ordinary programs. And when you wrote your gate segment, you could write it to be time limited or rate limited or record key limited or any other criteria that the gate segment writer chose. So for example, this means that in a medical records environment, you could easily write the gate segment so that it can only pull out the data associated with a single patient. And furthermore, you could only call it to pull it out every 5 seconds. So that if somebody managed to get in to the account of somebody who was authorized, they could only get out bits and pieces. And if it got called too frequently, the gate segment then basically did a, hey, somebody's trying to break in because they're running at computer speeds rather than at people's speeds. No, very, very easy to do. Now, once you had set up the access to a gate segment, it was callable by dynamic linking as a subroutine with a single instruction in the hardware. And so you actually wound up, if program A was calling program B and they were in the same ring, it took one instruction. If program A was calling program C and C was in an inner ring, it still only took one instruction and still took the same amount of time so that you could switch compartments very easily. All right. Questions before I move on to the next one? All right. Next slide. I indicated a moment ago that there was an access control list associated with each segment. And that indicated what kinds of access, read, write, or execute, and who had access. And all of this was mitigated through bits in the segment register, which was set up automatically the first time you call the program. This access control list actually had 3 parts: user, product, project, and mode. Let's look at the first one. The first one was a user. So if I'm a user, Dave is a user, Julie is a user, I can set it up so only one of those people or some set of those users can access it. Next slide, please. It has the word user on it. It's not. The second part and so when I created something, I automatically got read, write for myself and read, execute for me if I'm on a different project, but not write. The second part was project. So I could have different projects that I did for different companies or different groups within my company and access on my project. By default, when I create an item, it would be read, execute for all other users on that project. Yes, we'll show the second item, which says project. And the third item, which says mode. Doesn't seem to be coming up. It should be, next slide shows it automatic. It doesn't. So we go all the way to the, oh, there we go.
Yes, no.
It just took a little bit to come up. All right. So our third part was mode. All access control entries had a mode associated. Modes included I, interactive, absentee, they called it, we probably call it background today, daemon, system program running, and P with a proxy. Okay? So that means that if you manage to break into an account, you would automatically have a mode I. If there was something on the system that could only be modified in mode D, as all of the system code was, then breaking into a system administrator's account gave you no automatic access to change anything associated with it. In other words, there was no such thing as a super user or a super privilege that once you broke in, all bets were off. So one couldn't use the code of the system save or store daemon to comprise programs in the user storage area. And let's suppose, for example, I had something that was extremely personal to me that I didn't want anybody other than me under any circumstances to see. Why? When I created an object, I would merely remove permissions for the background processes. And hey, It's never going to go on a save tape. It's never going to be viewable by any system code. It's all totally private to me. I've just compartmentalized it to me. Of course, if I make a stupid error and destroy it myself, there's no backups, but hey, that's a trade-off. Okay, so the multiple factors on the access controls were important. Next slide. The next item I'd like to talk about is the system software installation. There was only one process on the system called the initializer sysdaemon that had write access to the system software areas. Nothing else did. So someone with authority, such as a user.sysadmin, had to send a secured message to the daemon, providing the piece of code that was to be installed in order to make this kind of installation and where to install it. The initializer looked at the piece of code that had been passed, such as, has it been built by someone on the system maintenance project? Was the request made during an authorized time frame? So for example, you could set it up such that you could only ask for changes to be made while in the afternoon, while a system admin would normally be present. The request comes from a process that's locally attached. In other words, if it can't be done across the network, it has to be copied onto a local system and specifically attached from there. And there are many other rules that you could do. All of the system software was either designed so it was deliberately changeable while the system was running. And yes, anything that a user could basically see could be changed while the system was running. Or was it something that because of its security implications could never be changed while the system was running, only by restarting the system? Okay. I'm going to ask for a show of hands on a question now. All right. So the question is, based on this, how often do you think they would have to reboot a multi-system? And I'll give you the normal times first before I ask you to do it. Once an hour, once a day, once a week, once a month, once a year, longer than a year. Okay, so how many think, like once an hour it might reboot? Once a day, once a week, once a month, once a year, longer than a year, longer than a year. Ian tells it, yeah, we made a few mistakes when we did it. That means that we have to reboot it maybe once every year and a half or so in order to change something like when we put a new major release of the operating system on, we have to reboot it. Because of course we can build it so you can be running version 10 and version 11 at the same time by different users. But when we want to force it so that all new users have to get version 11 unless they say which version they want, we have to reboot that system. Yeah. So multi-software system installation was extremely controlled. Very flexible, yet very controlled at the same time. Let's go to the next slide. The sixth compartmentalization was the resource management control. Resource usage, such as the amount of CPU time, the amount of disk space, how long you could be logged in, how long you could be connected, what shifts you were even allowed to log in was monitored and measured. Exceeding your quota wasn't allowed. You would deny the resources or force a session termination. For example, a user could only log in and run programs during their shift of work. And next one. So far, what I've been talking about is discretionary access control.
We can't hear the audio. Click it again, please.
We're all 5 after 2, we'll try and restart. Good idea. Well, you can tell that I haven't been regularly teaching. I could go way down where she wouldn't bother my voice.